So I will be talking about theory of large D membranes, and so the main context in which I would like to talk about is the second law of black hole thermodynamics. So just to give you a brief introduction for Einstein gravity, with the equation like this, we know that this black hole satisfies a set of thermodynamic rules. And from the set of those thermodynamic rules, one set is where TdS equal to D, the first law. This is the black hole energy. And from this definition, there is a definition of entropy that can be computed, which turns out to be the area of the horizon of the black hole. Now, for Einstein gravity, there is also a second law where which says that the area always increases during dynamical process. But we know that there is for this to be true, there is a constraint on the system, and namely that the right-hand side, which is the stress tensor of the system, needs to satisfy something called the null energy condition, which I have written here. And this is just saying that one component of stress tensor along any null ray should be positive definite. And once this is satisfied, we always find that during any dynamical process, the area of the horizon of black holes always increases, and hence the object which we call entropy from first law also satisfies second law, and that object is the area of the horizon. Now this is true for Einstein gravity, which is the minimal theory of gravity with two derivatives acting on the metric in the equation. Now for the story is a bit different for higher derivative theories. There is a first object which satisfies the first law, which you can call entropy. This is obtained by calculating something called the Wald entropy formula. And this calculates the entropy of stationary black holes. But there is a slight problem with the second law that, well, not slight, but a problem with the second law that there is no known candidate entropy for general dynamical situations. And even more, Wald entropy definitely doesn't satisfy the Wald second law, and we also don't know a candidate which does it for any general arbitrary dynamical system. Now there are some results where the entropy has been for dynamical process involving high derivative theories, involving black holes in high derivative theories has been calculated. One of the I will give you two nice examples here. I will tell you about two nice examples here. One of them is this situation where we concentrate on dynamics, which is perturbative in amplitude about stationary black hole solutions. For these situations, a candidate entropy exists, which has a nice limit in when you take the amplitude of perturbation to 0, which reduces Wald entropy, and away from the stationary limit, but limited to linear order in the perturbative in the amplitudes, the entropy actually satisfies the second law. And also there is for nonlinear dynamics, I mean, there is a special situation where the dynamics always preserves a spherical symmetry. And for those systems, these people actually found out a candidate entropy. But the point of telling you about this specific dynamical situation is that there is no known candidate for any possible dynamics that black hole can satisfy. That is, we have a first law for higher derivative theories. We have a candidate entropy for this, but there is no entropy which satisfies second law. Now, the broad aim of my talk is to, or the broad aim, not the talk, but in general, my broad aim will be to try to find a candidate entropy satisfying second law for general higher derivative theories of gravity. But this aim comes with a if at all it is possible to find one for any theory of gravity. And from the derivation for Einstein gravity, it looks like it was more or less I feel that magically happened that one actually found a candidate for entropy which satisfies second law. So it's not entirely clear that any theory of higher derivative gravity should actually have its entropy which satisfies second law. And the point is that if at all, if this is something, an important question to us, that we find that there are theories of gravity which do not satisfy second law. So one possibility will be to try, even if we think that this principle is strong enough that black holes in nature should actually satisfy second law, that the entropy should always increase in the process, then maybe we can constrain classical gravity theories using this as a constraint theory, allow only those theories which satisfy second law.
Can I ask one question, Arunabha, here? At least in the context of ADS CFT, if we are dealing with gravity in asymptotically ADS, one would expect the boundary theory to satisfy the second law, right? Because it's some theory without gravity, etc. It should satisfy the second law. So then wouldn't that make one feel that whatever is the black hole dual to the boundary theory at finite temperature, etc., that black hole also should satisfy the second law? And if higher derivative corrections are important there, or even if subleading need to be included, there should be a analog of the entropy for the black hole, including those corrections.
Let me try to give it, tell about this thing. In a context that I know about.
Yeah.
I know a little bit about. So one can most probably understand this problem in the context of fluid gravity correspondence. I'm not an expert, but I know, I like read about it. So there, in the fluid picture, which is the dual boundary theory, so there you can construct a entropy current, but there are constraints that the transport coefficient of the fluid must satisfy for the entropy current to satisfy second law. And I'm not sure if it is at all clear that any possible higher derivative theories actually satisfy those constraints.
I see. No, but you should go on. I don't want to slow you down. But what I wanted to say was, maybe one can't prove it, but we believe that typical field theories and so on, which unless they are sick, quantum field theories, etc., will satisfy the second law of thermodynamics,
sure.
Right?
But I'm saying that maybe there is not a field theory for any dual. For field theories which actually satisfy the constraint that you say, maybe there are no. Not all possible theories of gravity do not actually map to those type of field theories. You're saying something about
you say there could be consistent theories of gravity which allow for the second law to be violated. Is it you're saying?
Consistent otherwise. The definition of consistency depends on what sort of constraint you're putting on it.
Sandeep, I think he's saying that there are theories of gravity that you could write down that will not be consistent. And one of the diagnostics of them not being consistent is that they do not obey a second law. Such theories will not be dual to a unitary quantum field theory.
And then, just to understand, so perhaps what Arunabha is trying to say is that he'll write down various constraints which need to be met so that the second law is satisfied, and then any theory of gravity which is dual to a unitary quantum field theory should meet those.
Yeah, and perhaps even more generally, as you know, there have been other constraints recently explored, like these causality type constraints by Maldacen and collaborators. So, just Gauss-Bonnet gravity and Gauss-Bonnet looks consistent, but it violates that. So anything that looks consistent does not have the second law is not good. And perhaps there are other ways also of saying that same theory is not good. Maybe it violates causality or something.
Okay, thank you.
Yes.
One question. Please go ahead.
Sorry. One question, Arunabha, just about the logic. So when in the last line you say that allow only those theories which satisfy second law. Now, which second law? Doesn't this depend on the definition of the entropy? So what do you mean by this statement?
Yeah.
Because depending on what entropy I choose, I will be allowing different sets. It seems.
Sure. But the point is that can you write at least one entropy which will satisfy second law?
Okay.
Yeah.
Okay.
I have a question, maybe naive one. On the field theory side, what is the quantity that you would compute to see if this is being violated or not? just the entropy of the field, quantum field theory, is it? Or
Yeah. Sorry for the noise outside. I'm like, yeah, I cannot help it. But yeah, but the point is that I'm not going to do a field theory computation here. What I'm going to do is a different computation. I'm not working in ADS-CFT.
no, okay, no, I'm just saying that, like, if one, like, along the line of the question, like what Sandeep asked.
Yeah, so that's what I said. I can answer the question in one particular example. Suppose you consider fluid gravity correspondence and you try to construct at least one,
Okay.
given a fluid with a particular set of transport coefficient, at least try to construct one entropy current or one candidate entropy, which always increases in a dynamical process in the fluid side. So by the correspondence, you can always figure out like which theories will lead to this type of theories with fluids with this particular set of transport coefficient and which will violate this.
Okay.
Shall I go on?
Sorry, Arunabha, I still don't understand the logic here that is mentioned on this slide. So you say in the first option, you either find the entropy which obeys the second law, right? And then you say if it is not possible, then allow only those theories which satisfy the second law. But you don't have the entropy because you ruled out the first option. So just logic wise, maybe things will get clearer as you go on. Okay. But just to orient myself.
Yeah, just could I say one thing? In the study of fluid dynamics, you could have asked the same question, Abhijit. You could write down hydrodynamical equations and you can ask the following question: is there any entropy current that is always positive divergence on every possible motion of these equations of motion?
Okay.
This is a much analyzed question, and the answer to that question is no. There are constraints on the equations of motion that allow for any possible entropy current. Shantani, Loga, Mukund, Hongliu, various people have analyzed this. So I think this is the style.
I see. Okay, thank you.
Yeah, exactly. Thanks for the explanation. Yeah, so I will now go on. I carry on if there are no other questions. Now, in this talk, what I was trying to do is like, obviously, we can. I think at least I will say that this is a difficult problem because it has not been answered to its fullest extent till now. So I will try to go to a different limit in the parameter space of the theories, a different limit which is tractable, but it's not entirely empty. And this limit is the limit of a large number of space-time dimensions. And see if we can somehow use this to say something more about this difficult problem. And the thing that I will mostly that I will be using to actually say something about this problem is the duality between black hole dynamics and a non-gravitational system of co-dimension one membranes. I will talk a bit more about it later in the slides. And so what is this? This is a duality in which the gravitational dynamics of black hole in the large limit can be mapped to the corresponding dynamics of non-gravitational dynamics of particular co-dimension one membranes moving in the asymptotic space of the corresponding black hole. Now, what I will, as Shiraz already said, my style of approach to this problem will be to constrain the membrane dynamics and the dual membrane dynamics, demanding that the dual black hole actually satisfies the second law. Since I assume that there is a one-to-one map between dynamics, so if I can find a quantity which reduces to at least in some sense reduces black hole entropy and which always increases in the membrane picture, then I can use that to constrain the black hole dynamics. Now, if the constraints are not satisfied by the membranes, and I will show that, these constraints are not backwards. They can be really effective. For example, in a particular example where I consider Einstein-Gauss-Bonnet gravity, and I don't, in a particular limit, I will show that this combination of theory will actually violate the constraints that I get from this particular third step. So now I will go on This is the general line that I will follow. Now I will go into the details. Now, since I told you about the black hole membrane correspondence, let me briefly tell you what it is. So to see it, I mean, like the simplest way to see that something useful happens in this limit is to look at the Schwarzschild black hole metric in arbitrary dimensions, which has a blackening factor like this sitting in two places in the metric. Now, suppose if you are outside the horizon and you are at distances which are order 1, d to the power naught actually means order 1. And you take the large D limit. Since this number is less than 1 and you're taking a D goes to infinity limit, this will drop out. And it seems that you have landed up with f of r, which is 1. Now, this looks like that just outside the black hole, we are in flat space. So this looks trivial. I mean, like this is, but the point is that, as a discoverer of this phenomenon is sitting here with Robert, who I mean, like, figured out that actually one has to look at regions of space-time which are order R naught by D outside the horizon and not anywhere. And once you do that, suppose I mean I do that by choosing working a particular coordinate system where the distance from outside the horizon is parameterized by this dimensionless number R, which is order 1. And if you take the limit now, you will see that this blackening factor is non-trivial. That it has like, I mean, even though it reaches the flat limit exponentially fast in R, but it is non-trivial in this way. So to summarize what I said here, I mean, like, so for a Schwarzschild black hole with radius R naught, and there is this region of thickness 1 over D, R naught by D, which we call the membrane region, and the metric actually exponentially reaches asymptotic space-time towards the Augustine field exponentially fast outside this membrane region. And this is what we will exploit, I mean, like to exploit to arrive at this quality. And the point is that this form of the structure of the metric is actually also preserved in dynamical situations where you work in a situation where the I mean, you take a particular time direction and you calculate derivatives along that for this metric. If it is order D naught, order 1, then you still find that this structure is preserved even away from the static limit that I demonstrated. Now, what about nonlinear dynamical situations? So I modeled this nonlinear dynamic by putting some undulations on the horizon here. So local radius of curvature is LH. And there is, as I told you, there is still this membrane region where non-trivial warping of the space-time happens. And suppose if you concentrate on a small region around a particular point in this membrane region, let me call this X naught. The point is that since the space-time dies out very quickly to the asymptote as you move along this direction, so the metric definitely has a very fast direction away from the horizon. And derivatives of the metric along the direction is order of D. And this LH is to balance the dimension. Now, every other derivative acting on the metric, which is not along this direction away from the horizon, is order 1. So, I mean, to leading order in large D limit, this is order D, this is order 1, so this can be thought of as constants. So 0 to leading order in large D, every point locally around this point X naught, the metric around this region resembles that of the Schwarzschild black hole to leading order. And hence, one can use that phenomena to actually correct for the black hole dynamics to higher order. Now, how do you go about doing it? Yeah, please ask question if something is not clear. I mean, if whatever I'm saying is not clear. So locally, the metric actually looks like Schwarzschild black hole. Now, we want to exploit it, and we find it useful that to exploit this local Schwarzschild nature of the black hole, we work in a very particular coordinate system around that point X naught that we are talking about here, and this particular coordinate system is called the Schwarzschild coordinate system. in which the metric of the black hole actually looks a bit, it can be expressed in a nice manner where it can be written as a flat space-time part, plus the part which captures all the warping away from the wave. Now this can be written in a bit more coherent way. In this way. These two lines actually capture the same information. I'm not done anything new. Provided you make this redefinition that you call R by R naught as psi, TT as minus unity x, and so on. And why we want to do this is that it will be clear that we want to express our results as membranes moving in the asymptotic space-time, which is flat space-time here, and it somehow, I find that it is useful to actually use this form of the metric, or rather this form of the metric locally to actually arrive at the membrane duality. Now, how do we do that? So as I told you that locally, every point around any around any point in the membrane region, the metric looks like resembles that of the corresponding Schwarzschild black hole. But I have written it in a Schwarzschild form in a fancy manner. Now, suppose since we said that the leading order, the derivatives on psi, yeah. If now you elevate this function psi and mu as functions of space-time, with the only constant being that they are order d0 derivative, then you find that this metric actually satisfies the Einstein equation to leading order in large. So, the point of telling all this is that you can exploit the local nature of the space-time that it resembles Schwarzschild to actually arrive at an ansatz metric like this. Like you think that, make a guess that this may solve the gravity equation to leading order, and you find that that guess is true, provided some additional constraints are satisfied, which, if you look at carefully, these are actually also satisfied by Schwarzschild vacuum. And then once you have arrived at a nice guess, then you can add corrections at in 1 over d. And why add corrections in 1 over d? Because we exploited the large d to actually arrive at the fact that this was a solution. And then you can add these corrections. And the point is that the given any function psi and u, these corrections are obtained by only solving an ordinary differential equation in this variable r, where this psi function can be written in terms of this r function. So this is the main advantage of the large D. If you forget everything else, the main advantage of large D is that we need not solve for nonlinear coupled partial differential equation, which is what gravity equations are, and which we don't in general know how to solve. You are able to convert them effectively into ordinary differential equation acting on R, and hence, which is a problem that we have much more control over, and hence you can arrive at these corrections order by order in 1 over d. And hence, in principle, you have solved for the black hole metric in 1 over d perturbation series. And this thing, the fact that the set of partial differential equation actually get converted to a ordinary differential equation, this happens because the space-time has a fast direction. That, as I told earlier.
Sorry, Arunabha,
yeah.
I'm missing something. I understand why you have a fast direction, but there are many transverse slow directions, right? Which are transverse to this one fast direction. Isn't that right?
Yes.
And then the dynamics along the slow directions will be quite non-linear, no?
Yes.
You'll have to solve partial differential equations along those directions.
Yeah, but all those derivatives are order 1.
Those derivatives are order 1. But once you go beyond, say, your leading order, are they important for your 1 over d effects, or how important are they?
No, they are important. But the fact is that those transverse derivatives. Okay, let me show you this. Yeah. So these corrections effectively solved for are effectively solved by solving ordinary differential equation in this variable R that I showed you. But the coefficients of these functions in R actually capture the data that you say. These are capture the local transverse derivative data of the function psi and u. So, for example, I mean, like, let me try to give an example here. Suppose this function h mu nu 1, it actually looks like, suppose I am just cooking up this result. I'm not sure that this is something to. And suppose this is proportional to k mu nu plus some e to the power minus r grad mu nu and so on. But this is the result of the solving the ordinary differential equation disorder. And what I mean by this is that these things are evaluated only at the point x naught. And these things capture the derivative data, transverse derivative data that we are talking about. But the point is, since these are order 1 derivatives, and since I'm solving our particular point, so only the very local data, for example, this suppose this is obtained by action of, say, something like this is proportional to this. When you calculate this, this whole thing is order 1. But then there are like a coefficient of 1 over psi to the power d everywhere sitting in the matrix. When the derivatives act on this, they bring out factors of order d with various coefficients, which are ultra-local derivative data of the psi and u function that I got. So yes, you actually capture the transverse derivative data, and once you actually try to use this information to solve for the higher order corrections, then you will write the corrections as, suppose the d square of 0th order plus you write this 1 over d h mu nu 1. Now in this expression you write this 1 minus e to the minus r as 1 minus phi to the power minus d, because in the like this is the map between these quantities. You think of this k mu nu as functions, and then you solve for the higher order corrections on top of this. I mean, this is the same way that fluid gravity works.
Yeah, Arunabha, I think what Sandeep wants to hear is that in addition to the solving you're doing, you have to satisfy the Einstein constraint equations, and those will give you the membrane equations.
Yeah.
So you're absolutely right, Sandeep. You have to solve the additional equations. What Arunabha will do is derive the membrane equations from Einstein equations, but then you have to solve them just like in fluid gravity.
Right. Okay. Got it. Thank you.
I'm sorry for that.
No, I understand. Okay, thank you. I understand.
Sorry, before you go on, can I ask a simple question? So what is the starting point of this, what is the leading order equation, and how do you solve it?
What is the leading order equation and how do I solve it? Okay, let me see where I was. So as I told you, I'm still showing you the example in Einstein gravity. Okay, first of that.
Okay.
That the equation is, I'm solving for vacuum Einstein equation. The equation is simply that Ricci tensor is equal to 0.
Okay.
And it can be shown that this part of the metric actually solves for the vacuum Einstein equation to leading order in large T.
But this is some fixed solution, or there can be multiple solutions for this.
I mean, this solution has a parameter, like this functional degree of freedom. Like, in fact, 2 functional degrees of freedom. This psi is an arbitrary function, and in the definition of u, and this O mu is actually u minus n. U is another arbitrary vector degree of vector valued function.
I see. So for any such function, this will solve it, right?
Yes.
Now, when you do perturbation theory, why doesn't this freedom kind of come back to hit you at every order?
No, I want to use freedom at every order. Yeah, that's the whole point. That I mean, that's what.
So just fixing the solution at. Okay.
I'm saying that locally around any point, the metric can be written in this form.
Okay.
Okay, and once you have written that, you have this one scalar function worth of freedom and one vector function worth of freedom. Then you can systematically add corrections, which will solve for
Okay.
the Einstein equation order by order in 1/d. And the good thing about large D is that you only need to solve for ordinary differential equation to arrive at this corrections.
And then the final solution would be parameterized by these two functions.
Exactly.
See, these two functions obeying their equations of motion, obeying the membrane equations.
Yeah.
Okay. So that's what. Okay. That's the leading order, right? That's the leading order.
Yeah. I will tell you about that in the next slide. Yeah. But for now.
And just one sec, Arunabha, I think Abhijit wanted to hear that you can give a rather precise definition of the velocity and the shape so as to remove this field redefinition ambiguity you were talking about.
I will tell.
Right. Okay.
If it's okay, I can tell you in one of. It's there in one of the lectures.
Okay. Thank you.
Yeah. The basic point is that, and as Sandeep already guessed from it, that the black hole metric is a 1/d series in terms of the psi and u function. So given a psi and u, we can solve for the metric correction order by order in 1/d. And this can be thought of as being dual to a membrane, which moves in flat space-time, where the membrane is situated at psi equal to 1. I mean, the shape of the membrane is given by this. And the membrane has a local velocity degree of freedom given by this mu delta. Another point that Shiraz was alluding to was that, and now from this statement of duality, it seems that given any function psi and u, I can always arrive at a black hole solution. But that is not true. The point, and the reason is that not any arbitrary membrane configuration actually gives rise to regular black hole solution. And there are many ways to see it, that you need to actually impose constraints on the membrane data, which is the data of the shape and the velocity function, to arrive at a set of equations which are called the membrane equations. Once these membrane equations are satisfied by these psi and u functions, then you can always arrive at a corresponding black hole solution. Now, as Shiraz told you, these membrane equations are obtained by solving for the constraint gravity equations. I think this, if I'm not misunderstanding, this is what Sandeep wanted to know.
Yeah. Thank you.
Yeah.
I understand now.
So now,
also these membranes are always codimension 1.
At least the duality that I'm presenting in it, they are codimension 1. Yes.
I see, but could one consider more general things? And
I'm not sure, but I mean, I'm not sure if there are no such duality. But this is the duality that I am talking about. The membranes are order codimension 1.
Sorry, what do you mean by duality?
And duality means that I showed you that any black hole is dual. Any black hole with order 1 derivatives is actually equivalent to a membrane, and similarly, you can go the other way.
I see. Okay, thank you.
Now, to give a concrete example, the membrane equation for Einstein gravity. Yeah, so they are given by these two equations. Let me explain what these equations are. So these are obtained from the regular imposing regularity on the leading order metric correction. So these are so there are two types of equation. One is a vector, one which looks like a vector equation. One is a scalar equation. Now the vector equation has directions along these projectors, which are projectors orthogonal to the velocity direction in the membrane, because velocity is the only distinct direction in the membrane. Now, what are inside these membrane equations? So, for example, this is written. So, for example, this sigma is actually the shear tensor corresponding to this velocity vector field of the membrane. Kappa is a trace of the extrinsic curvature K mu. If you want to know what K mu is, K mu actually captures how the normal direction of the normal surface changes as you move along the surface. Or for very low dimension, for example, 1-dimensional curve, this is like the inverse radius of curvature. And the right-hand side written this way simply means that there are like lower order corrections to these equations. So this is the general structure of the equation for Einstein gravity. And actually they they contain the number of equations is actually matches with the number of degrees of freedom. That is one scalar degrees of freedom from psi and one degrees of freedom from velocity. So this look like consistent set of equation, and these have been used to arrive at many consistency relation, like they can produce the right quasi-normal modes for large D black holes, which have been derived in the gravitational picture by Roberto and this is all for the the memory equation. Now, why is this related to the entropy of black hole?
So sorry, those terms already then include dissipation, is it?
Yeah, that's what I will tell you next. That these are membrane equations. You can see that how this can be used to like tell you about dissipation.
I see. Okay, go ahead. Sorry to keep interrupting.
So now, as Sandeep already said, that I have to tell you why this has anything to do with dissipation. Now, the metric structure is like this is the answer metric plus correction. Now, as Abhijit, I think, wanted to know that what sort of functions are these? I mean, so obviously there is some redefinition invariance of this function that I can use. So I need to fix rather. So what one particular useful choice is that we demand that, from this leading order metric, we can see that horizon is at psi equal to 1. I mean, like by this, I mean that psi equal to 1 is the null surface. And generator of that null surface is the velocity vector. This is for this part. And this H mu needs to satisfy ordinary differential equations. So obviously, we need to set some boundary conditions on them. And we use the boundary conditions to make sure that this psi equal to 1 surface continues to be the horizon and u mu continues to be the generator of the horizon. Now, since we know that u mu continues to be the generator of the horizon, so and since we know that black hole entropy for Einstein gravity is proportional to the area, so the black hole entropy current is actually obtained by in a paper by these people. I mean, Chirag, Shantani, Anup, I guess, Mangesh, Umang, Utkarsh, and Somadip. And they found that among many other results, one of the primary results was that the entropy current for black holes in Einstein gravity under this map between black hole and membrane is proportional to the velocity vector, and the proportionality constant is 1/3. There are 1/d corrections to this, but this is the result. And so now, as Sandeep asked, like how is this related to dissipation? So you can see one of these equations is that divergence of U is 0 effectively to this order. So there is an entropy current which is proportional to U, and divergence of that entropy current is 0 to this order. So what? When you may say that the result at this order is a bit disappointing, like that in the fact that we did not find a dissipation at this order. But I think this is the general property of large D black holes with this order 1 derivative dynamic, that the leading order there is no dissipation. But we will show that dissipation happens at some order. Is it clear that this is how you can use the membrane equation to arrive at the dissipation?
I see. So to leading order, there is no dissipation there.
Yes.
Huh?
Yes.
Okay. All right. Thank you.
Can I qualify this a little bit?
Yes.
Because I think that's I mean, it's true that the leading order entropy stays constant, but this doesn't mean that in the leading order equations there's no dissipation. The equations are the equations can be written. They are kind of heat equations, so they are irreversible. So there's irreversibility already at the leading order equations. And one thing that one can find, it's something that we did for the particular case of the equations for a membrane, is to identify already at using the leading order solutions, you can identify a current whose divergence is non-negative, which turns out to correspond to what would be the entropy current at the next order. But you can identify it already with the variables that enter on only at the leading order. which is something that's kind of peculiar. That
Yes.
and the system, as I say, it's irreversible already at the leading order, so there's dissipation, but identifying a current that gives you, that characterizes this dissipation is something that's it's possible, but a little subtle. And I think, well, maybe Arunabha is going to say more about this.
Yeah. Yeah, but the point is that the information that the dissipation happens at the subleading order, even using the variable that Roberto said, that part is true, that it happens at subleading order, right, Roberto? Like
yes, that. I mean, yeah, I mean the identification of the source of the dissipation, it's probably done only at the leading, but already the leading order theory, that's a point that I want to emphasize. The leading order theory contains, with leading order variables, you can construct an entropy, well, a current whose divergence is non-negative.
I see. I see. So, oh, go ahead.
Yeah, maybe this is related to the fact that if you compute the leading order stress tensor, and you take the leading order equations of motion to be the conservation of the leading order stress tensor, then you do get this equation you're talking about.
Yeah, I think yeah, that's related. Yes.
I see. Arunabha, if it's too much of a digression, then forget it. But can you just show that equation of the membrane to leading order again, just so I can understand the comment that there's already dissipation? Is it easy to see? Is the reversing the arrow of time something like u mu goes to minus u mu, or what exactly is it? Is it easy to see, or?
I don't remember the redefinition that Robert is talking about, but like, yeah, there's one other. I'm not sure if it is satisfied.
Yeah.
You can calculate quasi-normal modes, and those even using these questions, and those turn out to be discrete.
So actually, that's what, when you said that it reproduced the quasi-normal modes, that's why I asked that question then. So it does reproduce that, including the imaginary parts of the quasi-normal mode at large D. So in that sense, it has dissipation in it, right? Yeah. But then the current is zero. The divergence of the current is zero.
Exactly.
I see. So it's interesting. Okay.
But divergence is zero at this order. Obviously, there is dissipation at next order.
And just to say again, there is a structure of these equations that makes it the conservation of a membrane stress tensor. And if you view the equations in that form, even at leading order, then there's this dissipation.
I see.
I mean, like what Shira is trying to say, that if you write the leading order stress tensor, and if you find the conservation equation, you will find that it actually reproduces the subleading order entropy production.
I see.
It produces the leading order membrane equation and definitely the subleading order entropy equation.
I see. Okay. Thank you. Please go ahead.
Yeah. So the question about entropy production. So if you look at the membrane equation at, by the way, how much time do I have? I mean, I know that usually it's of some sort, but I'm not sure now.
No, it's the same as usual.
Okay, thank you. Thanks.
Right. Yeah.
So the now the second law of membrane, how the second law comes from the membrane equation. So I told you that there is a vector equation, there is a scalar equation, and to answer this question, I need to only concentrate, at least in the way that I am trying to answer it, we need to only consider it at the scalar membrane equation. And since I told you already that the leading order entropy current is proportional to the velocity field, this subleading order scalar membrane equation shows that divergence of U is non-trivial. And another property of large D is that kappa is positive definite. I will not go into the details. I mean, I can tell you, but let's just assume that kappa is positive definite. And this sigma alpha beta is the variation of the velocity orthogonal to the velocity. So it has mostly, it has special components only. So this is also a positive definite quantity. And due to various orders in D of various terms, this whole term is actually order 1 over D. That's what I said, the divergence of U as order 1 over D. And hence, if you use the definition of entropy current, you will find the divergence of Js, the entropy current, is actually 1 over 2 kappa times this, and from similar argument, this is positive definite.
And sorry, Arunabha, so far you are doing Einstein gravity in large D, right?
Yes.
Okay. Yeah. Thank you.
Yeah. Once this is clear, I mean, like there is one can build on this too.
Right. Okay.
Yeah. So now, I mean, like, and it's more or less trivial to conclude from this line to this line that if you choose a time direction in the membrane wall volume, you'll find that the charge corresponding to this entropy current, which will be the entropy, is actually positive definite. Because this whole integrand, I guess, integrand is positive definite. Hence, the membrane equations lead to a second law, at least for Einstein gravity. So one may say that, I mean, like, even though one didn't put in explicitly the input of second law, but one obviously used the field equations of Einstein gravity, and one can arrive at the second law from the membrane equation. Now this I find promising. But what is the summary till now? That in the d goes to infinity limit, for a given membrane shape and velocity, there is a dynamical black hole. And the point is, the only membrane satisfying the membrane equations are allowed. Otherwise, this leads to non-regular black hole solution, which are not even black hole solutions. But the point is that every black hole in d goes to infinity with order d0 derivative dynamics is actually dual to membrane. Now, how do we see that? I mean, I have not proved it, but this is easy to see. I mean, actually, in principle, easy to see, not very easy to prove. That leading order black hole metric can always be written locally in the Schwarzschild form, because locally the metric resembles Schwarzschild black hole. So it can always be written in this form. Once we figured out how to write it in this form, we can figure out the function psi and u from here. Once you figure out the function psi and u, so you know what membrane leading order answer metric corresponds to. And precisely that is the membrane that you want to find the dual black hole. So this is a possible but difficult. I mean, some progress has been made by Shantani and her collaborators in various limits. And the final most important conclusion was that membrane equation actually know about the black hole second law. So let's see if we can exploit this to actually say something about high derivative. Now, I mean, as I think it is all clear that I want to talk about membrane entropy current for high derivative gravity, but the point is that I want to talk about membrane equation for only those black hole solutions which reduce to Einstein gravity black hole solutions in the limit when the gravity equation goes to Einstein equation. I think this is a reasonable assumption that you don't want spurious solutions in your theory. And then the point is to use the membrane duality to find an entropy current which has a positive definite divergence on shell, that you have used the membrane equation to arrive at this conclusion. And this entropy current has a smooth limit to Einstein gravity when the gravity equation reduces to Einstein equation. And obviously, I mean, as most people know that this current is by no means unique. I mean, you can, for example, one can always add a quantity to this current whose divergence is 0. It won't affect the result. But the point is to see if it is at all possible to find one current at all for any arbitrary membrane configuration.
So Arunabha, Arunabha?
Yeah.
Only the leading expression of the current matters for this, right? I mean, because it's a positivity equation, the subleading terms will not add to any constraint. Is that correct?
Can you say? I'm not quite sure I understood what you said.
I mean, this current presumably also gets some corrections, right?
Yes.
But I'm saying the current correction should be unimportant as long as this constraint equation is concerned. Is that true?
I mean, like, if you want to just compute the entropy, maybe that is true, but to make sure that the entropy divergence is positive definite, that is not very true. And this has to
you
do
need
with, yeah.
Okay.
Yeah, but
so you're saying you need these other corrections also.
Okay. This part you need, because large D actually works in a. I mean, like the way we take large D limit, it works in a way where divergences of vectors are one order higher in D compared to the naive derivative order.
Okay.
Yeah, so that actually is an important, that plays an important role in this construction.
Arunabha, I understand what you're imposing about the limit agreeing with Einstein gravity and all. It sounds like a good way to throw away spurious solutions. But just to understand, in a sense, are you taking the higher derivative corrections to be small?
No.
Or no?
I'm saying that you can take it to any value, but if you want to, in that, I mean, like it's suppose it's a parameter alpha. If you want to take the alpha goes to zero limit, at least you make sure that you only consider those solutions which reduce to Einstein gravity.
I see. There could be for alpha order unity, so to say, solutions which don't continue to the Einstein one, but which make sense, but you're not going to allow for those, in a sense.
Yeah, I'm not going to allow for this. Yeah.
Okay. All right.
So yeah, so now even though we will not be talking about a particular theory of Einstein gravity, but it helps. I mean, I will need some length scales to set up the problem. So it helps to work with the example of Einstein-Gauss-Bonnet gravity, which has an action like this. This alpha is there to balance the dimension of length between these two. This has a dimension of length. And this is the length scale below which the higher derivative terms can compete with R. Otherwise, I mean, they don't. Also, let us assume that the local radius of curvature of the horizon is order LH. Say LH is the thing that determines. And black holes will continue to have fast directions because, I mean, like, this is a general property of Einstein gravity, and we expect the solutions to smoothly match over to the Einstein gravity solution. So this the black holes in theory actually inherit this property that they have a fast direction. And derivative of metric is of the order of d by LH because LH is the length scale of the black hole. For example, if you look at the leading order unsurf metric, this d actually gave rise to the order d derivatives in the metric. Now, as I said, I demand that the theories of gravity should reduce to Einstein gravity in some way. But the point is that, as you see, the derivatives of the metric are order d. And there are more derivatives on metric here compared to here. I mean, this is 2 derivatives, this is 4 derivatives. So naively, if you just consider this to be order 1 thing and just count derivatives, these terms will overwhelm this Einstein gravity. And we don't want that in the equation. And how do we take care of that? I mean, like, obviously, we will scale this quantity. So this is, you can think of a sort of a kinematical constraint that we only want solutions which reduce to Einstein gravity. And suppose we consider the nth derivative term in the equation. So the n derivatives will give rise to a term like d by LH to the power n to leading order. And there will be since it's an nth derivative term, it will have a coefficient alpha tilde to the power n minus 2, just like here it was alpha square, to balance out the extra derivatives and match the dimension between terms. And this should be less than or equal to the contribution, leading order contribution from the equation of motion of Einstein gravity, which contains 2 derivatives, so 2 factors of d by h. And this, from this, if you manipulate, you can see that this alpha tilde by LH, this is the dimensionless parameter. In the problem, this should be less than order 1 over d.
So Arunabha, this requirement of solutions going over smoothly to solutions of Einstein gravity, it's more like the requirement of commuting with the large D limit, right? Commuting the alpha going to 0 limit with the large D limit. Isn't that what you're insisting?
Yeah, I am
rather than a smooth limit to the Einstein gravity. You should. Yes, because you are insisting that only at large D, right?
Yes, this is. I mean, the general principle is a solution should reduce to Einstein gravity, and in the large D limit, this is what you have to impose to get to that principle.
No, I mean, like, finitely this will happen, right? I mean, finitely there should not be a problem.
No, finitely you will not see this.
No, I mean, finitely this kind of constraint doesn't have any content, I'm saying, or does it?
I mean, finite D, I mean, there may be constraint. For example, I mean, like if you, if you consider a very large alpha.
Okay.
Yeah, then even there, these terms will dominate over this, right?
Sorry, and Arunabha, you want this inequality to be saturated if the leading order membrane equations are going to be modified, right?
Yes.
Thank you.
So, I mean, in a sense, you want alpha tilde to be, of order 1 over D, so to say, in LH units, but no bigger.
Yes.
Got it.
The sort of alpha prime, like the effective string scale is like 1 over D. In the sense that it's the string scale that suppresses corrections. I mean, by abuse of notation terminology.
Right.
Trying to avoid saying string scale.
I agree.
Okay. Now, how do I use this? I mean, so the trace of the extrinsic curvature of the membrane, which is proportional to radius of curvature, is actually equivalent to the temperature of black hole when the black hole is a stationary black hole. I mean, this has been shown earlier. And also the temperature of stationary black holes, it can be found that it's proportional to, at least static black hole is proportional to 1 over the radius of curvature, but the proportionality factor is D. So in principle, kappa is almost proportional to the inverse proportional to the length scale, but it has a factor of D. So now I want a dimensional parameter to tune in my problem in the membrane picture. And I arrive at it this way, that I say that alpha tilde K is the right dimensionless parameter. Why? Because I can rewrite it alpha tilde by LH times K. From this expression, we say the LH times K is order D. We know that alpha tilde by LH is order 1 over D. So this is the, multiplying all this, we find that this is the order D to the power 0 dimensionless parameter that we have in our problem in the membrane cell. And I said that, that solution should reduce to Einstein gravity in the limit when gravity equation changes to Einstein equation. And I take the limit by taking this alpha K goes to 0. This is the dimensionless parameter in the membrane picture, because I'm going to constrain the membrane equation. I will tell you why I need it. Now, there are vector and membrane equation, but mostly the thing that I will need, mostly, but not exactly true, but mostly that I need is the scalar membrane equation, which I claim has a structure like this, that is the sum of various terms, and these terms are formed out of the membrane data, shape, velocity, and we already saw one example in the Einstein gravity case, that this sigma mi was formed out of the sigma alpha beta. And the thing is that this side has a dimension of inverse of length, and I want these membrane objects to have dimension of inverse of length, and they are multiplied with this dimensionless parameter, dimensionless function, which is a function of this dimensionless parameter alpha K that I introduced. The example of this dimensionless parameter is like if you rewrite the Einstein gravity scalar membrane equation, you shift this part below this, and this is the M. There is one M in the Einstein gravity picture, and this 2 is the corresponding Fi for this Einstein gravity. And my point is to figure out the most general membrane equation, which will be a linear combination of all possible allowed MIs. MIs are the all possible allowed objects that can sit here, which are allowed by the higher derivative gravity. And similar principle also works for vector membrane equation, but we will need it to much lesser extent.
Arunabha, I don't understand as well as I should have already at this point. What all goes into MI? Presumably U and its variation in the transverse directions.
Yes.
And what else?
And psi and its variation in the transverse direction.
Psi. What was psi again?
Psi was a shape function. I mean, in the fluid picture, in the fluid picture, you can think of it as almost parameterizing the local temperature.
I see. Okay, so it's actually very interestingly similar. I mean, sort of like the fluid case, and then you're going to allow some appropriately high number of derivative terms here.
Exactly.
Okay, got it.
You've already finished the
So the derivative order of mi matches with the, maps nicely with the derivative orders of Lagrangian terms.
Can you say derivative order of what? Last
MIs
yeah.
Match, does it map to the derivative orders of these higher derivative terms in the Lagrangian, private Lagrangian?
Yeah, I will tell you more about that. I mean, like it doesn't really grow with the derivative number of derivative terms, but it gets cut.
Okay.
Hello, sir. Can I ask a question?
Yeah, sure.
So, if you consider non-stationary black hole situations, like in dynamical horizons or those kind of situations,
yeah,
could you write the dynamical horizon data in terms of a membrane data, which you are suggesting here?
Yes.
Okay. Is there any work which was doing this? Are you aware of any work which?
Yeah. So I think we have been writing papers for some time now.
Okay.
Papers are for large D membrane. So.
Okay.
And there is also other equivalent formulation of this. Yeah, this can be done. I mean, yeah. Now, so since I will not be working with a particular theory, so let me briefly sketch how I arrive at the most general membrane equation. So the black hole metric for general hydrogen theory in large D will take this form. I mean, like this form we are familiar with. These are the corrections. The most important part was to figure out the answer. But we will not exactly tell. I will not exactly tell you about what the answer metric for a given theory. But the basic point is that we assume that every theory has a Schwarzschild black hole. I mean, like we only work with those theories which have a Schwarzschild black hole, and also the constant that we earlier demanded from our theory. And that can be written in a Schwarzschild form to arrive at a form of leading order answer metric like this. And the constant on this function f psi, which sits here, is that the derivative of this function with respect to psi should be ordered. And this was true for the Einstein gravity, where f was 1 over psi to the power d minus 3. And this is what we demand. I mean, I think this is a reasonable demand. And also that f of psi should be 1. I mean, like psi equal to 1 is still the horizon. That the function f of psi. I mean, this is easy to check that if f of psi goes to 1 in this limit, then this happens. And then you like follow the similar procedure and arrive at the metric corrections for this particular thing. But we don't want to exactly evaluate this particular. The basic point is that membrane equations are determined by like objects that appear in the inhomogeneous part of the ordinary differential equation of relevant order. Why is that? Because these inhomogeneous parts of the differential equation is what will determine the solution of this type. And now I'm saying that regularity of these solutions will determine the membrane equations for you. So regularity where? Regularity everywhere in the membrane region. So those will obviously be these constants on these objects formed out of like various derivative acting on psi and u and so on. So once if you figure out like list of all possible objects that can be sitting in the ODEs, the ordinary differential equation of the corrections, then you can like use massage that form to somehow arrive at the list of all possible objects, membrane objects that can sit in the membrane. So this is the approach that I will follow. Another point is that higher derivative theory, I'm saying that they contain any arbitrary number of derivatives. I mean, and this is very useless if the number of derivatives acting on the psi and u function keeps scaling with the number of derivatives in the equation solution. Because I mean, like, I don't know then how to put constants on, like finite number of constants to see anything useful. Unfortunately, this doesn't happen. Fortunately, what we find is that there is an upper bound on the number of derivatives on the psi and u function in the inhomogeneous parts of the ordinary differential equation at each order in 1 over d. And there are various things that play a role in arriving at this upper bound. And one of them is that I consider alpha tilde, the string scale, so to speak, the ratio of string scale to the black hole horizon to the order 1 over d, and the fact that the various derivatives on the functions are ordered d naught.
So basically, Arunabha, unless all but a finite number of derivatives act on the fast part, then that term will be very highly suppressed, right?
Yes, exactly. Exactly. Because I mean, like if there are n derivatives, the highest possibility of d modulo the alpha tilde part that we can have is all the derivatives acting in the first part. Yeah, that will bring out a factor of d to the power n. But obviously, we have used the fact that alpha tilde by LH is order 1 over d to suppress that and make sure that it doesn't overwhelm the Einstein gravity part. There are then very few possibilities left, and then you can like figure out some bounds on how many possible derivatives can act on 7. Is this part clear at all? I'm not sure. Like, okay, I can go ahead.
Maybe I wait till Shiraz finishes, then I have something.
No, I'm saying you're basically saying that the 1 over d expansion is sort of like a derivative expansion on the membrane. It doesn't really matter what the equations are.
Exactly. Yeah. Well, it matters, I mean, to some order, but not beyond that.
Right. It's very similar in fluid gravity.
Exactly.
But you could change your equations of motion. You could put Gauss-Bonnet. Doesn't change the fluid expansion.
Yeah, but here it's a bit just minutely different because of large scale, because derivative expansion doesn't like.
I understand. Thank you.
But yeah, the basic principle is the same that what she has said.
But okay, now maybe I'm missing something, but isn't it? You are adding higher derivative terms, but up to some number of derivatives, right? Like for example, you may add 4 derivative terms or 4 plus 6 derivative, like that. Some finite number of higher derivative possible terms, if I'm right. Is that right?
Gravity theory can contain any number of derivatives, but the point is that this doesn't allow for any number of derivatives in the membrane theory. And yes, in the membrane theory, there is a finite cutoff for the maximum number of derivatives.
No, but that's what I was trying to understand. Okay, your underlying Einstein theory, you're allowing any number of derivatives.
Yes.
Huh?
Yes.
And you're saying in spite of that, only a finite number of derivatives will appear.
Yes.
This I am not sure that what was the reason now? Okay, maybe, of course, if the derivatives are acting on your fast direction, that is more important. I see. Okay, I got it. Because you scale the couplings of the higher derivative terms with 1 over d's appropriately.
So every derivative acting on a slow direction is effectively 1 over d.
Yeah, now I got it. Okay. Thank you. Yes. Okay, I'm with you.
So the summary is then that you can have as many number of derivatives as you want in the gravity theory, but you will, fortunately, will end up with only finite number of derivatives in the membrane side.
Okay.
Now, to give some examples of this. So, for example, if you are in the
sorry, just so I thought the scaling was determined. Scaling was fixed by insisting that Gauss-Bonnet and Einstein terms, they appear at the same order, right?
Yeah,
they compete with each other.
It is still fixed by that. But the last thing that I said is a consequence of that.
Right. So if that is so, then why is it that the higher derivative terms also wouldn't necessarily compete with Einstein gravity? Because this you're scaling it so that they do, right? So I'm a bit confused.
Okay, let me go back to that part where or maybe I can show it. Come on. I'm really sorry, but yeah, this is the point then. I told you that suppose this is the Einstein-Hilbert part plus some alpha tilde to the power n times the S gravity part, which has n number of derivatives. Okay. So now this part to leading order contributes order of d square by LH square. Because each derivative is order d, there are 2 derivatives here, and the derivatives are scaled by 1 over LH square. Because LH is the size of the horizon. Please tell me if you didn't want to know the answer to this. I mean, then I will stop. But thing is that now you can calculate a similar thing here. So there are order b to the power n by LH to the power n, because there are n derivatives acting on the metric. Again, like each derivative brings out factor of d, and each derivative also comes out to factor 1 over LH. And I wrote it wrong. Oh, sorry, this should be n minus 2. So this should be greater than or equal to alpha tilde to the power n minus 2. So from this, you can see that I just demanded that the leading order contribution to the Einstein equation was this, and leading order contribution 1 over d was this. So this simply from the fact that the left hand side should dominate over the right hand side, I arrive at the constraint that alpha tilde by LH should be less than or equal to order 1 over LH. Sorry.
I'm just asking, if it matches, if all the orders match here, why don't they match in the membrane equation?
I'm giving you argument for leading order.
Okay.
Okay. Now subleading order, not all derivatives. I mean, here I assume, as you see, that I assume that all the derivatives are actually giving rise to order d by LH factors.
Mm-hmm.
At subleading order, you don't want all of the derivatives to act on the fast direction. Otherwise, I mean, that already solved for your Einstein gravity equation at leading order. You want some of the derivatives to act in the transverse directions also. Those derivatives will be suppressed compared to this direction. But the point is, not many derivatives can act on this transverse direction, because you see at some, let's assume that the Einstein equation evaluates to order d by LH at the first subleading order. And suppose you assume that only some amount of derivatives actually act in the transverse direction, and not all. Suppose p of the derivatives act on the fast direction. Then you get d to the power p by LH to the power p. And only finite number of derivatives act on the rest of the derivatives act orthogonal to these, which are at least ordered d to the power 0.
Mm-hmm.
So you see, you're not left with many other derivatives acting in this direction, because you have to somehow match.
Okay. Okay, fine. Go ahead.
Now, so as I told you, the basic principle is to figure out the structure of the ordinary differential equation. Now, solutions of H mu are effectively functions of this function R. R is a parameterization of the psi. And coefficients of these functions are derivatives of the psi and u function. This is the structure of what I mean by solving for ordinary differential equations. Because effectively these are constants at given order, and you only need to solve for differential equation along this direction. Now, regular H mu I at a given order will be a constants on psi and u function, which in principle amount to constants on these functions. Now, there is slight difference between these two type of things. I mean, these are functions which derivatives acting in all possible direction in space-time. And these are derivatives which act only in the membrane wall volume direction, but that is a technical issue, and one can easily map, one can easily figure out what these corresponding things are once you know what are the possible things allowed in the ordinary equation. So this is what I mean. Like, you pull back the constraint equation on the membrane wall volume to arrive at the membrane equation. I'm not going to figure out like the membrane equation, but I'm going to figure out what are the possible things that can contribute to the membrane equation.
Arunabha, I'm sorry, I should have asked this earlier. You know, the transverse equations, or what perhaps Shiraz was saying, the constraint equations, not along the fast direction, but the transverse directions. What order are they in time derivatives? That is to say, like in fluid mechanics, they are first order in time because they are conservation equations of the stress tensor, you know, the constraint equations. Here, what order, before you added higher derivatives, just in Einstein gravity, are they second order in time or first order in time? Sorry, just to make sure I have the picture in my mind.
So I'm actually, my evolution direction is R, not the time. And the number of derivatives is actually determined by the direction of evolution. So yes, they are actually first order in R derivatives.
No, but that's your fast direction, right?
Yeah, but I'm doing evolution along the R direction. The Einstein equations The conformal equation have lower
suppose having solved to any order in R, you now try to solve the constraint equations.
Yes.
Sandeep, to leading order, they're also first order in time.
They're first order, huh?
To leading order, and then to subleading order, of course, there's the ambiguity about where you put the subleading corrections, whether you put in time derivatives or space derivatives, because you can use the leading order equations to move them around. But there'll always be a frame in which it's first order.
Okay. Thank you, Shiraz. Yes. Okay. Excellent. Please go ahead.
Okay. Yes. So now going back, suppose you follow the procedure and you figure out what are the possible terms that could have appeared in the ordinary differential equations. And from that, you figure out what are the possible scalar objects which could have, which could be sitting here at leading order in the membrane equation. And I say that an example was this Einstein equation, where this part was this. So the point is, once you have gotten to this set of all MIs, then the next task is to figure out an entropy current, which, following the earlier arguments, should have a limit to the entropy current of the Einstein gravity. So that's why I wrote it in this. So Einstein gravity entropy current was just u mu by 4 plus higher order correction. Here I'm allowing for a coefficient degree of freedom here, such that in the alpha k goes to 0 limit, this a of alpha k actually goes to 1. And similarly, this other coefficients also satisfy this limit that they go to the corresponding value in the alpha k goes to 0. And the point is that if you take the divergence of this object, so there is this part, I mean, like there are two parts coming from this only, and then the divergence of rest of the part. And from the equation of motion, I mean, like most general equation of motion that you can write, you can put here, you find that not all of them are positive definite terms. So they will not give rise to positive definite entropy production for any arbitrary dynamics.
Arunabha, remind me, this A is basically, this alpha is basically K, right?
Alpha.
I mean, its dependence on temperature and so on is on the dynamics is basically the extrinsic curvature, trace of the extrinsic curvature.
Yes.
Okay, thank you.
Yeah, this is the expression of alpha.
Yeah.
So now, since not all of them are positive definite terms, basic point is that you add some this f mu I, which I think it's a misnomer. I call it counter terms, but the point is that you take out the non-positive definite terms from here using this. And since I don't want to arrive at a unique entropy current, my basic line of thought is that can you figure out at least one, like whenever you think that this term is non-positive definite, can you figure out one counter term which will take care of the problematic terms? And if you are able to do that, then you have arrived at one possible candidate for entropy current, which has a form like this.
And are you using lower order equations of motion in what you're doing now?
Yes.
Okay.
Is there a problem with that?
No, it's good. It's good. I just didn't see in what you said where you were using.
Okay.
You're using it in classifying the possible terms, right?
Yes.
Okay, thank you.
Yeah, well, because yes, exactly. Now, the point is that if for a given f of I of k, that is a given term here, you cannot find a counter term. You just say that, that you have to put a constant on this coefficient sitting in front of this term, which I also like borrow the term from fluid gravity and called transport coefficient. Now, if you follow this procedure to leading order, there are not many objects that you can actually arrive at which can contribute to the leading order entropy production. I mean, even though I said that for the examples I know there is no leading order entropy production, but if suppose I don't know for all theories, maybe there is some theory where there is a leading order entropy production. The objects that could have contributed there are these not been like 4 possible terms. And I mean, even this term is like not really independent. I mean, like you can use the vector membrane equation to get rid of this. That I will show later. But
this A1, it was same as F1, F2?
yes.
Okay, okay.
Okay. So now if you follow the same procedure, what you find is that given this membrane equation, the counter term that you need to add to the entropy current is of this form. Like the form is not so important. Basically, the fact is that we can write a counter term. But the point is that you can only write a counter term for this 1, 2, 3 term. There is no counter term for this. There is no vector object whose divergence will give you something like kappa.
What was again that extrinsic curvature? Is it?
Yeah, space of extrinsic curvature. So yeah. So for large d, in the large d limit, we know that kappa is greater than or equal to 0. So even though there is no counter term, we know that this term is positive definite. So we can easily get away by simply demanding that the theory should have an A4 alpha k, which is positive definite. Now, as I say that I demanding that the theory actually satisfies the second law.
Sorry, the fluid dynamical analog of what you just said would be that the fluid should obey an equation of a thermodynamic equation. That is, if the pressure and the energy were independent functions, then you wouldn't be able to write down an entropy current. Is this right?
I think so, because but I'm not, yeah, but I'm not written on the stress tensor, so it will be difficult to picture that for me.
But probably, right? Shantini, does that sound right?
Is she here?
Oh, is she there? Oh, she's not there. Sorry. Yeah. Okay.
I see, but okay, you should go on. But if it's some constraint like that, then Shiraz, it won't depend on the nature of that equation of state. I mean, as to how you're saying some set of equations of state will lead to the condition A4 greater than equal to 0.
Yeah, I mean, if you just try to write down in fluid dynamics an entropy current, if you write down the fluid stress tensor in terms of energy and pressure, and you let energy and pressure be different functions of temperature, then in general, there's no entropy current. But if you write it down with pressure and energy being the functions related by thermodynamics, then there is.
Oh, I see.
It doesn't matter what the equation of state was, as long as it comes from an equation of state. Yeah,
yeah, but there is some.
I mean, at leading order, and then in addition, you need viscosity and conductivity to be positive.
So are you saying something like first demand equilibrium thermodynamics? Huh?
I think I'm saying that.
I see. Okay, okay. So then, Arunabha, that's an important point, no? I don't know.
But this is only at leading order. And then there are further constraints. Yeah.
Is there other constraint which since I'm not sure about this interpretation, let me go to the next page, then we can maybe come back. I think I need to be
okay. Yeah.
So now, yeah. So since I'm demanding that the black hole satisfies second law, so this simply means that the system is dissipative. So at some point, the dynamics has to stop, or rather, it can also begin from that place. So that is the stationary black hole configuration. And I demand that the system allows for this solution. So, and it can be shown that stationary black hole solutions are dual to stationary membranes. And what we mean by stationary membranes is that they have time-like Killing vectors in their world. And all membrane objects are invariant under B derivatives along this time-like Killing vectors.
Sorry, Arunabha, maybe it's obvious, but presumably the constraint A4 alpha k greater than equal to 0 is a non-trivial constraint in terms of the underlying higher derivative terms one can add, right? Namely, it is not going to be satisfied for all set of coefficients for those terms. Right?
That is what I'm trying to. I'm hoping that this will be useful to actually constrain the possible coefficient in front of higher derivative.
And do you actually expect that A4 will be equal to 0?
Yes. Sorry. I mean, like you're giving the talk for me. Thanks.
Sorry. No, I was asking a dumber question than you probably interpreted it to mean. What I mean is, suppose I write 4 derivative, 6 derivative terms with various free floating coupling constants. Scale them with D the way you want it to. but otherwise keep the coupling constants free variables. Now compute A4 in terms of them. Presumably the constraint A4 is greater than equal to 0 is not automatically met, right? It imposes some condition on this coupling. That's all I'm asking.
Yes, yes.
Okay, yeah. Go ahead.
Yeah. So, as I said, that there are stationary membrane solutions and black hole solutions, dual to stationary black hole solutions. And the stationary membrane are defined by presence of time-like killing vectors and invariance of the membrane objects under the Lie derivatives along this time-like killing vector. And one possible solution is that I could not prove that this is the only possible solution, but definitely one possible solution is that the stationary configuration is that the velocity field is proportional to the killing vector, time-like killing vector in the membrane wall volume. And by this configuration, it is easy to see that divergence of U should be equal to 0. Okay. Once that is true, we have shown that the general structure of the membrane equation is that the scalar membrane equation is that there is a divergence of U and it is equal to something. If the left-hand side is equal to 0 in the stationary configuration, all of the right-hand side quantities should evaluate to 0 in the stationary configuration. And some of these terms are quite easy to see that, for example, this is like by demanding that Lie derivatives of objects along killing vectors are 0, this is 0, but not all of them are like trivially 0 at station. So this imposes further constraints on these coefficients.
I see.
She has already guessed. And yeah. Okay, let me tell something before I tell what she has. So also the fact that I have chosen a particular velocity configuration. So the velocity configuration is not given, but there are many more membrane equations than to determine one scalar function. So by just demanding that all of the scalar functions don't give like conflicting solutions, I demand that all of them actually reduce to the same equation. And this imposes further constraints on the transport coefficients of the equation, and namely the vector membrane equation.
I missed this part. Could you just say it once more, Arunabha? What imposes further constraints?
Okay, so the point is that I've chosen one velocity configuration. Now there are vector equations and there are scalar membrane equations. But I am only left with the scalar shape degree of freedom to be determined by the membrane equation now, since I've already told you what my stationary membrane configuration. So all of these other vector membrane equations now should reduce to one equation, like a consistently determine a unique psi function for me now. And that will not always be true.
So couldn't it happen that you have to correct this ansatz to make that true?
Correct what ansatz?
U mu is equal to K mu. I mean, couldn't it happen that you have that, for instance, this is a choice of frame, right?
No, this is a choice of frame. That is all right. But I'm saying that the possibility that was that there is a stationary, there is a killing vector, and I'm saying that there is actually at least one solution which is proportional to K mu, which is definitely such that Lie derivative of U mu equal to 0. So this is definitely a membrane configuration, stationary membrane configuration. I'm not saying that this is the general membrane stationary configuration. For that.
But you're saying that in general, the scalar equation need not be obeyed for this, right? Or the vector equation need not be obeyed. Which one?
Vector.
The vector equation need not be obeyed. I see. So I was wondering, suppose it was not obeyed, perhaps you have to change U mu to U mu is equal to K mu plus delta, which is something else. That's not conceivable.
Yeah, I tried, but I mean, like this puts a very non-trivial constraint because you also demand that suppose U mu was, as you said, say K mu plus some beta mu. Then LK U mu would always be, I mean, this part I think is more or less trivial. LK of, LK of this part is 0. Then you have to determine that LK of beta mu is equal to 0. So you have to figure out a constraint for which LK of beta mu is equal to 0. And I couldn't figure out, I couldn't figure out a general form of beta mu.
I see. Maybe you're using the theorem that if you've got a killing vector field, that the only velocity vector field such that sigma mu nu and divergence of del is both 0 is a killing vector field.
Yeah, that is true, but I cannot use. Yeah, I would have loved to use that, but the point is that I'm not demanding that my entropy production is proportional to sigma mu nu square only.
Ah, yes. Okay, thank you. Yeah. Okay.
Okay. So this, I mean, like all this exercise simply says that, I mean, like this puts additional constraints, and the exercise is that, I mean, you can also write down the most general vector membrane equation and demanding that this set of one scalar equation, vector membrane equation, finally determine only one scalar function consistently, puts additional constraints, and also that divergence of u equal to 0. And these constraints are like this A4 alpha q, which we were talking about earlier, that is equal to 0. And one of the other constraints is that this A1 coefficient here is also determined in terms of this 2 and some other coefficient, A3 and some other coefficient. The point is that there are many other constraints on the membrane equation by demanding that the stationary is.
Good. So A4 equals 0, just from the demand that equilibrium exists, you got A4 equals 0.
Yes, yes.
Okay, thank you.
Okay, so the interesting parts comes at the subleading order. Now that was the analysis for the leading order. Now at subleading order, there are like many terms, like I think 18 or I forgot 21 transport coefficient. I am not writing that down. I'm only writing down the transport coefficient objects here, which for which I could not find a counter term. Okay, so there are these five terms which I think for which I could not find a counter term. Now, once you cannot find a counter term to these things, okay, so let me first of all explain what this term is. This mu means it's a product of like a contraction of acceleration of the velocity vector field. This is the sigma square, the product of shear, and this is vorticity. And this k mu nu pt is transverse stressless component of the curvature orthogonality union. If you are interested in the details, this final term is proportional to product of the sigma alpha beta, the shear, and the transverse stressless component of the curvature. Now, for all these four terms, we can see these all of these are positive definite, because these are, I mean, in some sense, they only have special components because all of them are orthogonal to velocity. So only constraint I mean, that would one require to impose, I mean, if this term was not there, was that all of these coefficients be positive definite, or there to be a second law, consistent second law. So these are what.
Can I ask you a question? Yeah. Are you using these functional forms of these B's, explicit functions of D11 or D10 or D5?
No.
But that involves a kappa, right? That involves a extrinsic curvature. So while you are trying that to find out a counter term, are you using those derivatives of those kappas?
Yes.
Okay. Okay, and you didn't got any, like the derivative of these B functions didn't appear in the expression.
I mean, even if you use that up, the point is that you cannot write a counter term from it.
I see. Okay. Thank you. Yes.
Thanks for the question.
Sorry, the derivative of the B functions are related to this mu by equations of motion, right, or not?
Sorry, say it.
The equation, leading order equation of motion, will relate mu to that derivative of the B function or not?
So what is mu?
Mu?
Oh, yes.
Right.
I think you are trying to say this thing.
I see. Mu, yeah.
Like in hydrodynamics, derivative of temperature is not independent data from acceleration because equation of motion related.
I see.
Yes, sorry for misunderstanding.
Maybe, yeah. That's why maybe there is no derivative. Yeah.
Yeah. So I mean, if you consider these terms, the constraints from second law are, I mean, I'm not yet talked about these four constraints, but then again, you can impose constraints from existence of stationarity, and you have to impose this additional constant that all of these coefficients need to put equal to 0 because sorry, this and this need to put equal to 0 because none of them vanish at stationary. I mean, it's easy to see that there can be a stationary rotating solution and stationary, like even rotation gives rise to non-zero acceleration and so on. And stationary membranes also have non-trivial curvatures. Okay, so now let's move on to this term. Yeah, I will not tell you the details, but the point is that if you are working perturbatively in this alpha k goes to 0 limit, and alpha k was the parameter in terms of which this transport coefficients were written. If you work in terms of that, you take it to alpha k goes to 0 limit and you treat it as a perturbative parameter, then you can always find a counter term for this object, but order by order in alpha k, that you always move the problem to the next order. But if you consider alpha k to be a non-perturbative parameter, that even if it is small, you consider it non-perturbatively, you find that there is no counter term. So constraint, and also the fact that this is a product of two different objects. So this, I'm not sure, it's not very easy to see that this should be a positive definite quantity. Hence, if you work with non-perturbative alpha k, you need to impose this constraint that b of alpha k should be equal to 0. And the fact that you can always correct it if you consider alpha k to be something very close to 0 and work perturbatively, and the moment you start considering it non-perturbatively, you don't have any consistent entropy current. It makes me think that this the radius of convergence up to which alpha k up to which there is a counter term is actually 0. That this problem of the entropy being not positive is actually a non-perturbative obstruction at all values of alpha. Now, all said and done, but the point is that are these constraints at all useful? So this is a here I can use a result that I from an earlier paper that I wrote with Yogesh Dandekar, where we worked out the membrane equation for Einstein-Gauss-Bonnet gravity, but perturbatively in the alpha k parameter. So the point is that if for as Sandeep at some point alluded that given a gravity theory, if you find particular values of these transport coefficients. These transport coefficients are determined by the particular theory of gravity that you're working with. Suppose there is a gravity theory which doesn't satisfy these constraints. And if you believe that second law is a strong enough constraint and existence of stationary solution is a strong enough constraint to impose, then from the EGB Einstein-Gauss-Bonnet computation that I'm saying, we find that B of alpha k is not equal to 0, at least perturbatively in alpha. But think that is non-zero even perturbatively in alpha k, it is definitely not 0 in general. But I'm not done the computation, but if something is not 0 in the alpha k goes to 0, definitely it's not 0 in general. So EGB gravity, when you consider alpha k to be a non-trivial non-perturbative parameter, it definitely violates second law second law of
Arunabha, I'm sorry, alpha k were the coefficients in the underlying Lagrangian. What was, I missed it now, I'm lost.
Alpha tilde was the length scale which multiplied it, and alpha tilde k is, you can think of it as alpha tilde d by L. LH was the radius of curvature of the local horizon, and you demanded that this be ordered d to the power 0.
Right. And this is your alpha k?
Yeah.
Okay, thank you. Go ahead.
So something that if you just consider, if you consider a world that has the classical gravity theory is just Einstein gravity plus Gauss-Bonnet gravity, it definitely violates the second law. Yeah. Well, I don't have much to tell.
I'm a bit confused. I mean, what are you saying in terms of the coefficients in the underlying higher dimensional theory? I didn't understand. I thought you would say some particular combinations I mean, there's some constraint on them, or are you? I didn't understand that conclusion. Are you saying? Are you saying what?
I'm saying that at sub-leading order, I mean, like at leading order, the conclusion was that you could write counter term for most of the terms. There was one term left, but you found that that coefficient of that one term has to be set equal to 0 from existence of stationary configuration.
Correct. So I thought that would impose some one constraint on whatever number of terms allowed in the underlying.
But that was for leading order.
Okay,
and,
yes.
But the point is that, I mean, if, the example that we have worked with, like Einstein gravity and four derivative series of gravity, the leading order Einstein equation, the membrane equation always turns out to be divergence of u equal to 0. That, I mean, by construction, those coefficients actually come out to be 0 for this particular example at leading order. At sub-leading order, these are the non-trivial terms. Non-trivial in the sense that I cannot write a counter term for any of these terms.
I understand. So then if they are not positive or positive semi-definite, then you say, I got to put the coefficients to 0. So you get so many more conditions, right?
Yeah, this is a sub-leading
order. Right. But in the end, do the number of conditions you get, how are they related to the number of possible higher derivative terms you can add up to any given order? Is there some analysis like that you wanted to do, or how did you?
So that I will, I'm going to show that this, I'm not done that analysis, but I'm showing that for this particular term, which I'm saying is special because you cannot write a counter term, and also this term, any part of this term is not positive, semi-definite. You have to put equal to 0, and I find that a given theory of gravity, that is Einstein-Gauss-Bonnet gravity, actually violates this constraint.
Okay. So Einstein-Gauss-Bonnet is out.
Exactly.
Okay, got it.
This is just a demonstration that these constraints are like, they actually do something on the theory of gravity.
Got it. Okay, very good. Please go ahead.
There's not much to say. So, and the point is that at stationary configuration, now you can impose one more constraint. For example, I said that I have put in this extra coefficient in front of the velocity field. Also, I said that there are terms that you can add in the entropy current, whose divergence is equal to, the entropy current is unique up to some ambiguities. Like you can, for example, the most naive ambiguity that you add terms whose divergence is equal to 0. The point is that now you can demand that the membrane entropy current should match with the corresponding wall entropy at stationary. And if you do the leading order analysis, leading order in large D analysis of this, you simply find that it's always possible to tweak around this A of alpha k to actually make sure that at least at leading order, the entropy current that you find satisfies both second law and also matches with wall entropy for the corresponding. But for what happened for Einstein-Gauss-Bonnet gravity is that you just land up with a non-zero B of alpha k, and it definitely doesn't satisfy the second law itself. And that is all I had to say. So
okay, Abhijit has to go, so I'm taking over as the chairman of the session. So questions.
So, Arunabha, how powerful is the constraint? Okay, you ruled out Einstein-Gauss-Bonnet, but to put it slightly differently, along the lines perhaps prompted by Shiraz's observation of connections with causality bound, suppose I were to restrict the corrections to fourth order in derivatives. Well, in 4D, you have two possible combinations, right? Gauss-Bonnet and one other, right? If I'm right. But all right, in higher D, I suppose you might have three. I'm not sure. Anyway, okay, you keep all four derivative terms. Is any combination of those terms allowed, or are all four derivative theories, if you have restricted up to four derivatives, ruled out?
The point is that
Go ahead.
I think there are 3 independent coefficients for 4 derivative theories that one can.
Okay. And then if I allow arbitrary combinations of those, I demand that, the entropy in large D is increasing, etc. Am I allowed any combination of those at all?
Yeah, I have to say a bit more about this. So the point is that if you consider this theory to be perturbative in the higher derivative parameter, I think only then you can write a Schwarzschild black hole solution at all order. At least.
Suppose I took the view, I'm not saying this is particularly well justified, but I take the view, that's it. It's only up to 4 derivatives and nothing more.
No, I'm saying that if you consider this parameter perturbatively, only then you can write a Schwarzschild black hole solution.
Sandeep is saying he doesn't know how to write down Schwarzschild black hole solutions for the most general theory you're interested in. So he won't know how to do the analysis.
Oh, with the 4 derivative terms. Huh?
With Gauss-Bonnet, there's an exact solution.
Yeah.
Oh. Even when you scale your couplings with this 1 over D and all, right? Because I suppose they are still order 1, actually.
The point is that you can always find the solution perturbatively in parameter, but up to even then there is a. I at least suppose we are concentrating only up to linear order in the parameters. Okay, you can find a black hole solution. I've written down the membrane equation for that. Okay, so I'm not worked out the membrane equation at first subleading order, but I'm assuming that since B alpha k coefficient came out to be non-zero for Einstein Gauss-Bonnet, it will be non-zero for there also. I mean, in the limit where it works, and it will impose one constant to these 3 parameters.
And otherwise, so let's do it perturbatively just for a moment. We construct the solution perturbatively, we examine the constraint. You say there's only one constraint in 3 couplings.
No, there is only one constraint which I definitely know is violated. I also showed you some other constraints where is it? Yeah, these constraints. Since I have not worked out the membrane equation at subleading order for this general theory, I don't know if these are violated or not. But the fact that it is we can write a perturbatively, the point is that you can write a entropy current which pushes the problem to 1 order higher in alpha k. So if you are happy with that, you can write an entropy current.
But okay, then you push it. But I was just wondering, all right, suppose I say this is it, up to 4 derivative alone, can you just rule that out? Namely, then will we be led to the conclusion once you allow any number of derivatives beyond Einstein gravity? It sounds too strong, but I'm asking. Once you allow any number of derivatives beyond Einstein gravity, demand the second law, then you have to allow arbitrarily high number of derivatives.
I would hope that is true, but I'm not sure.
Okay. All right. Okay. Thank you. Thank you.
More questions? Sorry, just following up on that. Why did you stop at second order in the 1 over D expansion? Why did you stop at this order?
First of all, it was getting late. Writing a paper and it's a bit difficult. Otherwise.
What? Sorry?
It was taking up a lot of time to write even up to this order, and that's why it's a bit difficult to actually list out all possible terms. And
but you don't. It's not because you feel that there are no new constraints at the next order.
I just lost patience.
I see. Now, just again to follow up on that, Shantini has this sort of classic result in hydrodynamics that that says that any theory that obeys the constraints of existence of equilibrium, any fluid theory that obeys all the constraints that come from the existence of equilibrium, plus also have a positive viscosity and conductivity. So that the equilibrium both exists and is locally stable. For every such theory, you can write down an entropy current. Do you think something like that is true here? I suppose what I'm asking is this condition that B is equal to 0, can one see it just from existence of equilibrium somehow or not?
One way you see, it's very difficult because at equilibrium, this goes to 0.
Right. in order to get Shantani's result, she needed to consider not just equilibrium, but also adiabatic.
Exactly. I'm not done that. So,
yeah, I was wondering if you did the analog of that, you could see this more straightforwardly.
yes. But
I'm sorry. I should have known this, but Shiraz, she proves this arbitrarily far from equilibrium then, huh?
Yeah, she proves that once these conditions are obeyed, then no matter what solution you have of hydrodynamics, entropy will always increase, no matter how violent the solution is. It's amazing, right?
I find that kind of mind-blowing. I mean, I'm sorry I'm registering this only now. Gosh. Okay, that sounds incredibly powerful. I see. All right. Wow. Okay, go ahead. Yeah.
And just one more follow-up. The difference between these equations and hydrodynamics really is the existence of this K-mu nu.
yes.
And it's sort of interesting that your particular term involves that K-mu nu in an important way.
Yes.
So perhaps there are more. The result from Shantani was that if you do equilibrium, nothing else really is there. And it's sort of hard. It's harder to believe that equilibrium black hole solutions don't exist, right? In general theories, but perhaps because of this K-mu nu, it's more powerful. It rules out more than you rule out in fluid dynamics. Sorry, this is a vague question, but I was asking you for your feeling.
But I missed the point of the question.
The point was that Shantani's result tells you that if you milk all the conditions from equilibrium, then there's just inequalities left. All the equality kind of information comes from equilibrium.
Yes.
And then the dynamics after that just gives you some inequalities.
Yes.
You are getting an equality, right? You are saying B has to be 0.
Yes.
Now, I was wondering that whether, I suppose the same question again, but the fact that you use K-mu nu makes it less clear that the fluid dynamical intuition will hold.
Oh, I see.
So I'm wondering whether just, the analog of Shantani's result is more constraining. Yeah. I say this because it's hard to believe that you take a reasonable equation of like Einstein-Gauss-Bonnet and equilibrium solutions won't exist, right? Of course, we know they do, right?
They do.
So somehow the structure of these equations look like they must be more constrained. Like the analog of Shantani's result should be less generous somehow.
Yes.
I'm sorry, it's just a vague question. No, not even a question, vague comment.
Yeah, I'm seeing that. I mean, at least from the equation of motion, I see that. I mean, like B of alpha k equal to 0 is definitely not coming from stationary constraint, and it comes from really like the dynamical issue of second.
Yeah, so somehow the fact that you're doing hydrodynamics on a moving surface, and probably the fact that the temperature is not an independent degree of freedom, energy density is not an independent degree of freedom, right, makes these equations very tight, is what you're saying. It's hard to satisfy the second law.
Yes. So I didn't think of this earlier.
I think I have the feeling that's what you might be saying.
No, I'm saying, yes. I mean, like if you impose second law, then you have only that imposes B of alpha equal to 0. Stationarity doesn't impose this constant B of alpha. Right. And yet we know that in hydrodynamics, there's nothing like this. Right? Yes. And it's nice that K-mu nu is involved in a deep way. Yes.
Yeah. Okay, thank you.
No, thank you. I mean, like I didn't think of this.
One last question. Do you expect that if you use the alpha prime expansion from string theory, do you expect these equations to be obeyed? Suppose I do to first order in alpha prime. Then do you expect B to be 0?
I don't know. Do you get like just Einstein-Gauss-Bonnet in any effective theory of string theory?
You see, my question is ill-defined because string theory only exists up to 20.
No,
10 dimensions.
Oh, so, let it be. Let me say that D equal to 10 is. I am ready to do a 1 over D expansion in D.
Okay. Yeah.
I mean, like, do you find an effective field theory where just Einstein gravity and EGV gravity comes?
not Gauss-Bonnet, but let's say you do the heterotic string, you would get something like Gauss-Bonnet and the other terms, right? The other two derivative terms. You'll get some with particular coefficients, like Sandeep was asking. And then you could just take that and compute B.
Yes. In principle, yes.
Okay.
But
But I'm just wondering, let me just say, I was just wondering whether you would find that not even string theory would obey it. Because you're doing a 1 over D expansion.
Yeah.
So maybe what you will end up proving is that in D equals infinity, the only consistent classical theory of gravity is Einstein gravity. There's nothing else.
Maybe.
Because we know string theory doesn't go up that high.
Yes.
So why not? Maybe that would be a fantastic result. Right?
Yeah, but the string theory constants, which confine us to D equal to 10 or 26 or whatever, are not really classical constants.
You could say that. However, the Virasoro-Shapiro amplitude, if you take it and expand it, if you take that amplitude and you expand it in poles, you find the coefficient of the poles goes negative above a dimension.
So, you're saying tree processes are classical?
Tree processes are classical. So even in tree level amplitudes, you see problems.
I see.
Okay. I mean, so I mean, yeah.
It will be very constant, yeah. But what I'm trying to say is that this can be used as an example so that it's not always clear that. I mean, at least for example, if someone says that they have at some point they have an expression for entropy which satisfies second law for any general theory of gravity, one can definitely take this limit to see that maybe either I am wrong or that analysis is wrong.
Right.
That's what.
Okay, other questions? Okay, that was a